Exercise 41.19. This exercise is to be solved manually. Consider the region enclosed by the graphs of x squared minus 4y squared equals 4 and 5x minus 2y equals 14. Part A. Sketch a quality graph of the described region. Provide a graphic approximation of the area of the region. Part B. Provide a calculus calculation that yields the exact area of the region. Part C. Assess the correctness of parts A and B by examining for consistency between the two results. Part A. Sketch a quality graph of the described region. Provide a graphic approximation of the area of the region. Let's do a preliminary investigation of the graphs of these two equations to see what sort of coordinate system that we'll need to make a nice final graph. So for starters, this first equation here. Alright, this equation, two variables, quadratic in both. We know it's a conic section, and just from even this form, with x squared and y squared having opposite signs, we're thinking hyperbola. We should probably now try to write this in standard form for hyperbola. It's almost there. We just need to divide both sides by 4 so that a 1 will be on the right hand side. And if we wanted to be really explicit about the standard form, we could go one more step and write the 4 as a 2 squared and the 1 as a 1 squared. Alright, now here's where we need to recall the basic information for a hyperbola written in standard form. In this case, we'll have a hyperbola which has a horizontal transverse axis. Its center will be at 0, 0. The distance from the center to the endpoint of the transverse axis will be 2 units. The slopes of the asymptotes will be plus or minus 1 over 2, 1/2. Since we are going to want a rather high quality graph of this hyperbola, we would like to have a few more points actually on it in addition to the vertex or vertices. One way to get a couple points quickly, although you have to remember a few other things, and that is to use the latus rectum. Its endpoints are on the hyperbola. So two things to recall there. One is center to the focus is the square root of a squared plus b squared, or in this case that's the square root of 4 plus 1, the square root of 5, and then the length of the latus rectum, well, and generally speaking, that's 2b squared over a, and we can compute that in this case. So again, we're just trying to get a rough idea of what's going on here. So maybe just a thumbnail crude sketch of this information. Oh, something like that. Let's go ahead and look at the other equation and see if we can't detect what is going to eventually be the bounded region here. Okay, linear two variables. Of course, this is a straight line, and just maybe two quickie points would be to get some intercepts here. We let x be 0, and let's see, then y is negative 7, and then if we were to let y be 0, x would become 14 over 5. That's about 2.8. Okay. And then adding this onto our thumbnail sketch. Okay, 0, negative 7, let's see, 1, 2, 3, 4, 5, 6, about there. And 2.80, that's about there. Okay, so we have a line that looks about like this. Okay, so for our nice graph, it looks like the enclosed region here is straddling the x-axis, sitting here in quadrants 1 and 4. And so it looks like we would do well to sketch a coordinate system that just has quadrants 1 and 4. And since it's all rather congested here, maybe we spread things out and scale things with 1 centimeter equals 1/2 unit. Okay, let's do that. point. To get a nice hyperbola sketch here, it looks like I would like to have at least another point here. So this way I'll just get the old-fashioned way. I'm just going to let x equal 4 and see what y becomes. That y-intercept is a little off the coordinate system to be of use here, so let's instead try something else, like perhaps letting x be 1. Alright, we also have here two important points of intersection. Let's go ahead and get those calculated. Okay, so for the points of intersection problem, we have here this system of nonlinear equations, and looks like the substitution method looks most promising here. Let's take this second equation and solve it for, say, x. And then we can substitute this into the first equation. Alright, and looks like we're going to need to expand all of this and eventually end up with a quadratic equation. Okay, with this, it's before proceeding any further, of course, let's make sure we have some graphic consistency with this. Looking back at the graph, if we have a y equals to negative 3/4, we find that actually looks about right. And how about a y equal to 4/3? That also looks pretty good, consistent with the graph. So let's keep going and find the corresponding x-coordinates to these by just making use of this nice equation here. Now let's look at the graph again and see if an x equals to 5/2 is consistent with the y at negative 3/4. Yes, looks good. And how about having an x equal to 10/3 going along with a y equal to 4/3? That looks correct as well. Okay, let's go ahead and label these on the graph. Okay, and now we're finally ready to graphically approximate the area here. Okay, as a plane geometry shape, I want to take advantage of this straight line here, and this part of the hyperbola is pretty close to being a straight line. I think I'm going to work off of this. Let me make a dashed line here to get started. Now I think triangle looks like a pretty useful geometric shape. I'm now going to try to sketch in the third side in such a way that the little overflow here just fills in the void left here. I think about that should do it. Okay, and fortunately this graph is scaled the same way both in the x-axis and y-axis direction. So this geometric shape, although it's rather oblique here in nature, I can just use ruler measurements to pick off the base and height of this triangle, and everything should be fine. So here's our basic idea here. So the area of the region is about equal to the area of this dashed line triangle we have here. And like all triangles, we could say that area is 1/2 base times height equals 1/2 of, okay, the base of this triangle. Now remember that our scaling here is 1 centimeter equals 1/2 unit. So when we measure this 2.1, we'll call half of that about 1.1. The altitude or height of this looking to be, okay, about 4.1. So that will be half that. Let's say 2.1. And then, okay, a little arithmetic. Okay, 1/2 of 2.3, we'll call that about 1.1 square units. Alright, this is the main conclusion of this part A here. So a nice prominent cloud to mark it off. Alright, time for an analytic calculation. Part B. Provide a calculus calculation that yields the exact area of the region. Alright, let's decide on a strategy for an analytic calculation of the area of this region. Initially, we might try going with the most popular method of calculus, and that is to try slicing up this region with thin vertical rectangles. Let's try that. Okay, looks like two issues have developed here. At first, the things look pretty good. When we look at the tops of the rectangles, we see that the same red curve is determining the tops of each rectangle. So that's great so far. When we start to look at the bottoms of the rectangles, however, first issue is that the same red curve is determining the bottoms of the rectangles in the beginning, which is actually not too bad. In fact, we could take advantage of the symmetry of the hyperbola and only take the rectangle down to the x-axis and then double the result to get our calculation. That would work and work well. However, a second issue develops about halfway across the rectangle sequence, and that's where the bottom of the rectangle is now defined by the blue curve, or the blue straight line. Now this gives us a second definite integral to have to create, and we can do it, but maybe there's an easier way. So let's go ahead now and take a look at slicing this with thin horizontal rectangles. Okay, this looks much better. This time, if we watch the right ends of the rectangles, we find that in each case it's determined by the blue straight line. If we watch the left ends of each rectangle, it turns out each is determined by the red curve. So this is looking pretty good as a strategy. All we need to do now is formulate the area of a single rectangle. Let's do that. Like any rectangle, the area will be length by width. In this case, the length of the rectangle will be its right-hand x-coordinate minus its left-hand x-coordinate. The width of the rectangle will be a little piece of the y-axis we can call dy. So we've decided on this strategy, a definite integral that sums thin horizontal rectangles, and to sum those, we're going to be summing up x right minus x left times the width dy. Okay, let's start putting together the specifics here. So as a first subcalculation, let's go down here, perhaps, and let's work on the x right and x left. Okay, we're looking at the graph, the x right, that's being determined by that blue line. Blue line's equation is 5x minus 2y equals 14. Okay, solve for x then. Okay, and the x left. Okay, that's determined by the red curve, whose equation is solving this one for x. So initially we have the two formulations for x here. Okay, graphically, we are looking for the right branch of this hyperbola, and in this case, the right branch has x's which are positive. So that leads us to x being only equal to the positive version of this. Okay, let's bring these two sub-calculations up to the main line. Also, while we're thinking on it, the limits of integration C and D, again looking at the graph, since we are having width dy, we worry about where y begins and where it ends, and from our graph it begins at negative 3/4, it goes up to 4/3. Okay, now to go further, it appears this integrand is not going to get any simpler. We're not going to be able to collect any like terms here or anything. It's probably best we break this into two problems, two integrals, and evaluate them one at a time, since they seem to be rather different looking. So here we can say, and refer the reader to a second collection of subcalculations, which we can go to now. Alright, so here's the first of these two definite integrals, and this one pretty straightforward for finding an antiderivative, just a simple power rule. So let's do that and perform the arithmetic. Okay, this about settles the first definite integral. So for the second one, okay, in this case, we could try to get an antiderivative right away. First line of strategy is always to work off of your basic forms, the ones you have memorized, and for most people, that would not be a success here. The second line of strategy is to consider u substitution. Okay, what would you try? It would probably be to try u equals y squared plus 1. Then du becomes 2y dy, but we're missing a y factor. So that pretty much defeats a u substitution. Okay, other strategies. We've got this radical here, and the radicand is a y squared plus 1. Okay, we got a chance to eliminate such a radicand because we could use a trig substitution, and that would help us out. So let's proceed to do that. Now that means in trig substitution you don't substitute in the limits of integration and just proceed forward as in a u substitution. You want to take the indefinite integral problem aside as an entirely separate issue. So we'll do that here. Now we'll use this bullet to indicate a subcalculation within a subcalculation. So starting at about, I'll say here, let's just work with this problem. Okay, and as far as a trig substitution goes, we could come in here, we could have y equals 2 tan theta. The reason is you're thinking ahead that you want to see some trig identity make this a perfect square, and if y is tan theta, this becomes tan squared theta plus 1, known as simply secant squared theta. Now, a really thorough trig substitution includes the domain. So what about theta? You know you want secant theta to be positive, so that when you simplify the square root of secant squared theta, you don't need to have absolute value signs anymore. Thus, we always pick the domain here to be theta lying between negative pi over 2 and pi over 2. And, of course, dy, that's going to be secant squared theta d theta. Okay, so here's what we have. Now, as we mentioned, this here, that's going to be secant squared theta, and then we can take its square root as being secant theta, no absolute value signs needed, and this brings us to, okay, and well, now what? Alright, it's a trig integral with the secants here. One of the first lines of strategy is to try to factor off a secant squared theta d theta and have the remaining factors be tangent thetas. Okay, if we factor secant squared theta d theta off here, the leftover is a lone secant theta. Okay, not successful. The other type of strategy here is to factor off a secant theta tan theta d theta. That's not really available either. So what have we got left? Not much. We can try integration by parts. Sort of a desperate maneuver, but it might very well work here. Okay, first a little memo as to the integration by parts, and that's u dv equals uv minus v du. Now here we want to have a dv be something we can easily get v from. Okay, so in this case here, the only thing that's going to work easily is to make secant squared theta d theta be dv. And then it'll leave us with a choice of u to be secant theta. Okay, so v will be tan theta. du, that's going to be secant theta tan theta d theta. Okay, let's substitute that into here and proceed to claim this to be uv secant theta tan theta minus v tan theta du secant theta tan theta. Okay, slight simplification of this. Now, what about this here? If you factor off a secant theta tan theta, you get left over with a single tan theta. Too bad. Alright, the other option, factoring a secant squared theta d theta, no, that's not really available either. Okay, maybe we exchange this tan squared theta in by making use of that same identity, tan squared theta plus 1 equals secant squared theta, which would allow us to trade this in for secant squared theta minus 1. Alright, then if we did that, we could then break this into two separate integrals. Okay, now this one we can get using basic form. Okay, so this, you want to have like all of the single trig functions in your memory as basic forms, and secant theta d theta, okay, indefinite integral natural log of secant theta plus tan theta in absolute value. Okay, so we've got that. Then this, okay, oh, but you know what? This is the quantity that was at the left-hand side of this equation we've been working at. So what we actually have then is an algebraic method right now, and that is to add secant squared theta d theta to both sides, putting two of them on this side, and this side has all solved expressions basically. So we have here that this implies that, okay, and of course just divide both sides by 2. Alright, and now we want to do our back substitution. For that, you usually sketch yourself the angle theta in a right triangle. Now our original substitution was y equal to tan theta. Okay, so y has to be opposite over adjacent. Y to 1 gives us this theta, meaning the conditions is that tan theta equals y over 1, or y. And then Pythagorean theorem tells us this side is y squared plus 1 squared, y squared plus 1. Okay, now we can use this as a device to back substitute everything we need. So this becomes 1/2 secant theta, okay, 1 over cosine theta in other words. Cosine theta is adjacent over hypotenuse, so the reciprocal will be the hypotenuse over adjacent, or a square root of y squared plus 1. There's tan theta, that's y. There's secant theta again. There's tan theta. Okay, and since this was an indefinite integral, there, now we have a completely correct equation. Alrighty, great. Now, we want to take this result, in fact, or more specifically, we want to take the simplest of all these antiderivatives here, the one with c equal to 0, and bring it to our original equation of this. So let's do that. Now when we substitute our result up to here, or we bring our result up to here, there was a 2 here, so that 2 will now cancel with the 1/2 to make just a 1, and simplifies things a little bit for us here. We're ready to claim that this equals 2. Okay, and now it's just substitution and arithmetic for a while. Okay, and there's our second result that we need. It's time to bring back both these subcalculations to the main equation line. Alright, so here, the result of our first definite integral, that was the 875 over 2 to the 4th 3 squared. And now we're subtracting the second definite integral result. Okay. These have the same denominator. Alright, that's nice. Okay, and this, with the square units, becomes our calculus calculation result. Okay, let's go on and assess the correctness. Part C. Assess the correctness of parts A and B by examining for consistency between the two results. Alright, to assess correctness, let's go back and take another look at what our graphic approximation for the area was. That was 1.1 square units. And now let's take a look at our calculus calculation again. It was 35 over 12 minus natural log 6. Alright, to get an apples-to-apples comparison, we'll need this calculus calculation as a decimal number. Let's see, 35 over 12. Alright, without actually doing the long division, that's really close to 36 over 12, which is 3. 1/12, really similar to being 1/10, so calling that 2.9 is very close. And now this natural log 6, what about that? Again, this is a manual solved question, no calculator. So what to do? Okay, let's think about logs at the most fundamental level. Log is an exponent, and we know that the natural log of e, for instance, would be 1. And e, what is e? It's about 2.7, right? Okay, so we know log 6 is more than 1. Something else we could say, and that's natural log of e squared. That would be 2. Almost the same as, let's see, e is about 2.7. Let's do 2.7 squared. Okay, so that's about natural log of 7.3. Alright, now since we're after natural log of 6, 1.8, something like that, right? Okay, and what's this give us? This is 1.1. Okay, now although we had to kind of do a little conjecture here on this natural log of 6, still probably no exaggeration to say these results are within 10%, since this is a conjecture here, and that means these are really consistent. And so it's very likely that the calculation's 2 parts A and B are correct. Okay, so these two results, considering the conjecture for natural log 6, are probably within 10% of each other and thus consistent. Therefore, the solutions to parts A and B are likely correct. Alright, and you really do need a check for consistency to walk away from this question. I didn't show this, but I had 2 inconsistent results before arriving at this third and final consistent one. So there's a lot of chance for error in a rather complicated question such as this. Okay, very good.